Hello students, Ms. Slyman here. So the even day students had a chance to discuss ambiguous case with us in class, but odd day students didn't get to have that chance, and so I wanted to come in and sort of do the extension of the warm-up that I did with the even day classes. And even if you're an even day, maybe you want to see this again. So there's often going to be times that we just give you two sides and an angle, and those are going to be in the relationship of side, side, angle. And this is when you need to be really careful because it's possible that, so in giving you the two sides and the angle, it's going to be side, side, angle. So this angle is fixed. I can't move it. So I have to keep this proportion. This side length is fixed, so it's also going to stay there. But this is like a hinge joint, and so this second side, while I know the length of it, I don't actually know which way it's pointing. This third side, I don't know the length of, so it could be anywhere here. So if this second side that I've been given is too short, no matter how I swing it, so let's see if I can now move this. Nope. All right, so I'm going to erase it. And so if that second side is too short, then no matter which way I swing it on that hinge, I'm never going to hit this side down here. So if that second side is too short, then I'll end up with 0 triangles. If the second side is really long, then I'm going to end up with just 1 triangle. So if it's really long, it can only touch here, because if I tried to touch it anywhere else, it's under the third side, because this angle, remember, is fixed. I can't change the angle. Now, there's going to be some times that the side is the perfect length, and oh no, can I not erase that? Well, okay. There's going to be some times that this side is the perfect length, and so it can touch here, but it could also have swung out over here. So in this situation, we end up with 2 triangles. The triangles I care about, though, are this smaller one here. So I care about this one. But then I also care about the one that's created with this side and this other pink side. So then the other triangle becomes, let me create a, different version of red. So I also care about the same side over here, other pink side, and now this side, the full side in the bottom, which overlaps that other bit. And so now I want, this is a bit too dark still. Okay, so now I want, why is that still? Oh, I didn't actually choose it. That's why. Silly. Oh, goodness. So now I want this triangle that overlaps that little side I found in the bottom, overlaps this angle as well. So I've got all of this. And I don't care about that extra isosceles triangle formed on the inside by my swinging sides, but it is an isosceles triangle on the inside. So technically this is 3 triangles, but only 2 of those triangles have all of the sides that I wanted. So let's look at ways to make this happen. So I think the best rule to use for this is cosine rule. The reason I think that is that cosine rule is a quadratic, and I know when I solve a quadratic, I'm going to have 0, 1, or 2 solutions. So if, for example, I told you that angle B was 15 degrees, side B was 18, side C was 7. Well, I have on opposite sides of my cosine rule, I have angle and side length. So I'm going to make 18 squared equals a squared plus 7 squared minus 2 times a times 7 times cosine of 15. I put that into my calculator and solve it. It's a quadratic. We get 2 solutions. But we know, of course, that a is a length, so a has to be positive. Not the highlighter tool. So I can only draw one possible triangle, and so now I'll come and draw it. Tiny angle of 15 degrees, side C is 7, side B is 18, so it had to swing out the far way. I know that A is an obtuse angle. I know that C is acute. So when I come into my calculator to solve, I want to make sure that I'm solving. So let's come in here. And I'm going to go into my menu, actions, and I'm going to clear my history. I'm also going to go into doc and look at my doc settings because my calculator's been doing some funny stuff. So doc settings. Instead of having exact calculations, I'm going to come in and say approximate because we know that we're going to end up with decimal answers with this. All right, so in this case, if I solve for angle A or angle C, I want to tell my calculator whether it's an acute angle or an obtuse angle. And the reason why is that if I just put this in my calculator as is, so I like to use the integer values personally because I don't want to have to go up and copy a whole bunch of decimals. So I'm going to go with sine C over 7 equals sine 15 over 8. So I'm going to solve sine C over 7 equals sine 15 over 8. If I just hit enter now, oh, we got to tell it that we're solving for C. It gives me a whole bunch of things that look crazy. And that's because we know that angles are periodic. Sine function is periodic. It just keeps repeating itself. So I actually have to tell my calculator, okay, this is what I want you to solve, but I want an acute angle. So control equals to get my such that symbol, such that 0 is less than C is less than 90. And now it gives me just one value, 13.08. So angle, did I do something wrong? Oh, it should have been 18. Okay. Over 18. And we get 5.78 degrees. We always want to give our angles to the nearest tenth, whether in degrees or radians. Oh, 5.78. And then I can just use the idea of my triangle to add them up and solve. Okay, so now let's look at a scenario where we end up with more than one solution. So this is now a new problem. So now side B is 10, angle B is 37, side C is 11. So if I solve this in my calculator, I get 2 answers, both of which are positive. Tells me I can draw 2 separate pictures. So I'm going to make, rather than put them in one picture, I'm going to make 2 separate pictures. So my angle is what I'm going to start with. 37 degrees looks something like that maybe. And this side is going to be so this is my 37 degrees. And that must make this angle B. Across from B is side B, which will be 10. And I'm going to make it come way back in because side A is 1.23 basically. So this will be angle A. Side A is going to be that little bit of 1.289 ... So across from angle B is side B, which is 10, and side C. So now this is my first position of C. That's my first possible angle for A. Well, it can also look like when A swings out the other way. So same angle measure, same 11, but now my 10 is going to come out here. Oh, shoot. My 10 has to go a little bit further. Let's just connect it. All right, I'm going to call that 10. And now this side is 16.28. Here was where the original C1 was. So this distance here would be 16.28 minus the 1.289. This is my second possibility of C, my second possibility for angle A, my second possibility for side A. This is still 37 degrees. It's the only possibility for B. And I'm going to show you how we could use some geometry to help us, so we only have to do the sine rule once. So I'm going to do sine rule using the acute angle A up here, or the obtuse angle C down here. Doesn't matter. So let's set it up so that I don't have to use my decimal. So 10, I'm going to start with angle on top, but that doesn't matter either. Sine 37 over 10 equals sine of C over 11. But here I know that C is greater than 90. So I'm going to come into my calculator. I'm going to solve sine of 37 over 10 equals sine of C over 11, solving for C. And this time I'm saying 90 less than C less than 180. So we have to give it both values, or else you're just going to get the repeating solution like we had up here. All right, C is 138.55 degrees, approximately. All right, that means that this angle here, so right there, I'm going to come in and call that alpha. So angle alpha is 180 minus C1, because that's a straight line there. Well, remember that this side 10 could have been in here, which made this isosceles triangle there, which means this angle is the same as this angle. So C2 is equal to alpha. Yeah. So this was my angle C1. C2 is going to be 180 minus that. So I'm going to come and copy this, paste, maybe. No. Obviously it did not copy. 548. There's my 41.452. So 41.45 degrees to the nearest tenth. And now I can come in and figure out what my angles A are. So A1 is going to be 180 minus angle B minus C1. A2, 180 minus angle B minus C2. So I only had to use my sine rule once to find all my angles. So in the scenario where we would have something that had no solution would be if this side was really short. So let's say that instead of having C be 11, C was 1. I just want to show you what that would have looked like. So we would have had a solve 10 squared equals 1 squared plus A squared minus 2 times 1 times A times cosine of 37. We would have tried to solve for side A. Missing a parenthesis, okay. Oh, because it's not cosine times 37, it's cosine of 37. Wow, I still managed to get an A length. How is that possible? I don't believe it's true. If that was side 1, it's saying. So clearly I've drawn my 37 to be too big. Is that possible? There's ways you can check this on the internet. We can go into a triangle calculator. Did I really make one up that has, I'm going to be shocked if I did. All right, so we had an angle, let's delete this one out. Angle B was 37 degrees. Side B we said was 11. Nope, side B we said was 10. Side A we said was 1. Units were degrees. Oh my gosh, it did work. Wow, how small would we have to make? Oh wait, I don't want side A to be 1. No, what happened? Oh, it rearranged. No, it didn't rearrange my angles. What happened? Let's do that again. Side B was 37. Oh, we said side C was supposed to be 1. But it's still going to work. Man, that's crazy. Let's make our angle even bigger. So if we had, let's say, a 60-degree angle, it still worked. Amazing. Okay, believe me that there's going to be times that you get no solution and it's not going to work, I promise. And in that case, you would get 2 negative solutions, or you would get something that says invalid or false, something like that. But cosine rule will tell you if it doesn't work. All right, hopefully that helps you with some ambiguous case stuff. As always, feel free to keep putting questions in our document or come to office hours, and we're super happy to help you.